Welcome to part 2 of Unified Supply Chain, part of the X-Celerate webinar series brought to you by ISQ. I'm Paul Kotzer from Business Development, and we'll be running through the demonstration. So for the case study, we've selected a magnetite and pellet plant. And the challenges is we want to minimize shipping costs from the rail and the ships, and we want to optimize the production schedule. It was then modeled in very much detail with all the constraints associated with those points in the software. And then it is also run to minimize the financial impact on all of those. The results is speaking for themselves here. And there's a good example of the amounts that were saved by using this implementation. Let's look at how it physically works. Unified Supply Chain first opens in its unified environment where we can see the various models that exist. Planning or scheduling phases shared reference data such as definitions of models and the various products that exist in the system, as well as tools that interact with the server. Unified Supply Chain is built on a client-server arrangement where the user normally views the various models and run the optimizer to save the changes back to the server. The updated information is then available to other users. Opening the planning case launches the optimization environment, but before we look at optimization, we're going to look at the physical model itself. Here we can see the supply chain model with all the various components of the system. We have the concentrator, which produces magnetite slurry that feeds the pellet plant. This produces several different pellet types. We've got to divide them between live piles and dead piles. The concentrate and the pellets are then railed to the port where they have the product stockpiles. These units can be added from a standard toolbox which enable us to drag and drop the various components that make the supply chain. When we open any of these components, we can see various information behind the scenes which defines how these components operate. This is a highly configurable system. That means that the optimization can always remain aligned to the actual operations of the supply chain. During optimization, the various choices of what to produce and where to send material will also be explored, so that overall the highest value results can be achieved. Now we look at the operation environment. Firstly, we see that there is a series of periods defined. In this case, it's set up to run for a month. We have various kinds of input data that define the starting conditions. This includes things like the feed of the concentrator, the daily downtime that applies to all the equipment, operating rates, and so on. Starting inventory levels would typically be provided by production management. Here we have various kinds of raw input data. Clicking on demands, we can see the ship data. Each demand is representing of the cargo of the ship. Ships have additional parameters as well, such as the time of arrival, the rate to charge for demurrage or dispatch, the operating rate to use for the calculating the marriage, and there's various other factors. Most of this input data is set through integration so that the user doesn't have to manually enter any of this information. Having checked that the input data is correct, the planner or scheduler can run the optimizing having clicked on the optimization button. The clock starts to record the time of optimization. Now that the run is completed, we can see that there are some parameters showing overall metrics for the solution. The most important of these is the objective function value, which is the overall profit that's been achieved with this plan. We can now start to look at results, and one of the key areas to look at is the ship loading sequence. Here we can see the ship loading over time of the daily tons loaded starts with ship 1, followed by ship 2, then 3, and so on. We have then a gap between shift and it goes on to the next ship and so on. Ships are not essentially loaded in order. However, the optimizer is free to change the order of the ships to achieve the greater profit. For example, you can see that it's gone from 5 to 7, then back to 6. It then jumps to ship 10 and back to ship 8, because this was the higher profit scenario for the plan. So this is the overall loading of the ships that took place. Now let's look at upstream to the production sequence on the pellet mode page. We can see each of the different pellet types that are produced each day. It starts with type LSA, swaps then to DR, and then a couple of days of SAP, back to DR, and then several days of LSF. The objective here is that the optimizer is ensuring that the right product is produced to meet the ship demand without delaying the ships. But at the same time, it's trying to minimize the amount of chopping and changing between products because it costs every time you change the pellet type. It is therefore a balancing act between production costs and trying to minimize demurrage costs. Other areas we can look at the rail product so that they can see that the tons being railed each day. You can see that typically more than one product may be loaded on a given day. There are other rail KPIs as well, such as the loading time for various components. And finally, we've got the number of operating drivers and locos. These are all certain constraints on them which can't be exceeded. In addition to the results like these in tables, it's easier to look at using graphs. In this case, we're looking at the final inventory at the end of each day. Useful examples to view as line graphs. So for now, each of the different pellet types or concentrate types, we can see the daily inventory build-up. We can also change this view as a stack bar chart, which is useful for viewing total inventory in different types. This is the inventory in the loadout. We can see the same sort of thing at the port. After the planner or scheduler has reviewed the results, they would most likely like to make some changes and rerun the optimization. So, for example, it could be that one of the ships must start later because its arrival time might have been delayed. So on the other parameters page, we can see the ship's one arrival time was 6 days ago, but suppose that ship was delayed. We set to arrive in 4 days' time into the planning period. We then rerun the case. We get the following results looking at the ship period tons over time. We can see that the ship 1 has now been delayed so that they're only starting to load at the start of day 5. It is therefore very easy for the scheduler to make appropriate changes to the overall constraints of the solution to achieve the necessary profit objectives. And this brings us to the end of part 2 for Unified Supply Chain, part of the X-Celerate webinar series brought to you by ISQ. Please reach out to us and come and visit us at our Customer Experience Center, where we showcase the latest technology for the connected industrial ecosystem. Please reach out to us if you want more information, and thanks for watching.